Okay, so here we're going to take a look at discrete structures. Now, we are not going to just kind of an overview here. We will kind of go back to these throughout the semester, right? But here we're just going to introduce when we say structures or a discrete structure, what are we talking about here, right? So the first one is this idea of a set, right? Now we could probably spend the semester talking about sets and what all we can do with sets, classifying and all that. But here, a very general definition here for a discrete structure is, when we say set, is something that is an unordered collection. Right, so there's going to be no order here to the collection of objects, usually numbers, but not necessarily, right? So when we say we use this type of notation, like for example, that would be a set, all right? Just a collection, right? There's no order to it, right? The set could be finite, like we have this here, or it could be infinite, where here we have, or we could say something like this. All right. Okay. And sometimes, so using also other type of notation. So these numbers here, 1, 2, 3, etc., right? Those are what called the natural numbers, right? Started here that we call natural numbers from starting at 1, right? And going on to just infinity, right? We can also kind of provide more detail or more restrictions to the type of set in using this type of notation. Right, this is called set builder notation. So when you write something like this, right, where here the way you read this is that x is a natural number, right, such that, right, these two little dots here, x is less than 10. Right, so this is just another way to write 1, 2, 3, 4, 6, 7, 8, 9. Right, strictly less than, right? So it does not include 10. So we could do that. Right, now there's different things that we can do with these sets. We can describe them as union, right? So let's say that set A is the numbers 1, 2, 3, 4, and set B are the numbers 1, 4, 6, 8. All right, and if we can think of this as A, this is set A, this is set B. All right, so in A we have here 1, 4, 2, 3. B we have 1, 4, 6, 8. Right, so I wrote it in this way here, like a Venn diagram here, so we can kind of illustrate here when we sometimes say A, this sign union of B, all right? So we have A union of B, this is the, both of these combined, right? So A union of B would involve 1, 2, 3, 4, 6, 8. Right, so that would be all the elements in A and B. Right, so this is union. Then we also have this other notation, the intersection. Right, so now the intersection, that is what is in both of these. So this would be something like 1, 4. Okay? And then also we have something else called a subset. So when we say subsets, right, let's say of A, right? If A is my set 1, 2, 3, 4, subsets of A would be maybe just 1. All right, let's use another letter here. 1, 2. Right, so these would be subsets of A, right? So they contain the elements of these subsets come strictly from A, right? And all of the elements in the subset must be elements of A. All right. So those are sets. One other thing about sets is we have this term for sets that we call cardinality. Right? And what this essentially is the number of elements in a set. All right. Okay. Now, sometimes, right, kind of building from these sets, we want to match numbers from one set to another, right? And now one way we can do that is via another discrete structure known as a function, right? So a function is a rule, just in the most general terms, right? So a function is a rule where each input has exactly one output. One output. Okay. Now, we can use the very general notation here. The f is the name of the function, and then these values x and y are the corresponding sets, right? It is a rule from set x that gets mapped onto set y, right? So, and again, we're used to these in algebra, for example, something like this. Right now here, since we're dealing with a discrete type structures, then we're not really interested in an interval of values, but we most generally can think of, if we're thinking of finite sets, we can make this rule the set of 1, 2, 3, right? This gets mapped onto the set y, right? Now, if we're taking the double of x, right, the set y would consist of 2, 4, 6. Right, so that's one way to represent this function, right, using the above notation. Right now, if we take the set x, right, 1, 2, 3, it's called the domain, right? Our inputs, the set of all inputs is a domain. Now the set of all outputs, 2, 4, 6, right, if we're mapping these on here, right, this is usually called the codomain / range. All right, now if we talk about one particular instance, like here 1 gets mapped onto 2, right, so f of 1 is equal to 2, this value 2 is the image of 1 under the function, okay, and we can pair it like an ordered pair, right? Now this is different than a set, because in its name, ordered, it's an ordered pair, right? Whereas before, when we said a set, the order doesn't matter. For an ordered pair, it is very important, right? Hence why it's called an ordered pair. All right, now kind of building off of that here, functions can come in two different ways. We can either have a closed formula where here we just simply need to know, right, the value, which value in our domain to give us the image, right, or a value in the range. Now there's also, so this is called closed formula, right? We also have something called a recursive formula. Okay. So here, now, in order to get the recursive depends on knowing the previous value, right? So we have to start with some kind of initial condition. So let's say that f of 0 is equal to 2, all right? And in order to come up with next values or other values, the nth value, it would be necessary to know the previous value, right? So for example, I already know what f of 0 is, so the way I would calculate f of 1 would be 2 times this n minus 1 is just the previous value. So n minus the 0 value, which I know to be 2, which is 4, right? And then f of 2, right? 2 times f times the previous value, so f of 1, which is 4, 2 times 4, which is 8, etc., right? So this is this idea of a recursively defined, right? In order to find a value, I need to know what came before, right? But I also need to start with with some kind of initial condition in order to start this recursion formula here. Okay. All right. So those are, and again, right, I'm just kind of, it's an overview of the structures that we're looking in throughout the semester. We will be going in depth into each one of these types of structures, right? So the next one is what is called a sequence, right? So this is just an ordered collection of elements. All right. So we can think of an ordered triple or an ordered pair, right? Where we have here, right? So this is a sequence, right? A very basic sequence. So now this is different than this. All right. So this ordered triple 1, 2, 3, right, is different than this ordered pair 3, 2, 1. Right. And again, this is in contrast with a set, right? Where if I wrote the set notation, 1, 2, 3, this is equivalent to 3, 2, 1. Right? So while here, these are different because order matters in a sequence, these here, they are the same because order does not matter. Right now, with order mattering, that means that we can kind of use subscripts here to refer to an element in the sequence. All right, so putting them in order, we can say A0, A1, A2, etc. Right? We will be dealing both with finite and infinite sequences here. So sometimes it will be an order triple, finite, or sometimes it'll just keep going, infinite. Right? And the type of notation, shorthand notation here would be A sub n, where n is greater than or equal to 0. This tells me where my sequence starts. And sometimes, alternatively, we'll say n, element of the natural numbers, right, in an ordered way. Right? And similar to fractions, similar to the functions that we talked about, we have closed formulas where I simply need to know what value I'm calculating the sequence term for. So closed. And then I also have recursion, where we can specify a previous value or the initial value, sometimes two initial values. And then our recursion formula would be here. Here, right? Essentially, you're adding up the two previous terms, right? This is a very famous sequence, right, called the Fibonacci sequence, right, where you just take the next term is found by we're giving the initial conditions, and then you just add up the two previous terms, right? 1 plus 1 is 2. 2 plus 1 is 3. 3 plus 2 is 5, etc., right? And that's what this formula is telling me here. All right. All right, so those are sequences here. Right. Now, another structure is this idea of a relation. Okay, so now a relation is it's different than a function, right? So for example, if I take the numbers 3 and 9, right, and relation is a way to relate these two numbers, we could say 3 is less than 9, right? 3 or 9 is a multiple of 3. Or 9 is 3 squared, right? So all of these are relations between 3 and 9, a way to kind of relate both numbers, right? They are not equal in this sense here. And, different than a function, right? A function, each input maps it onto one output, right? It's a unique image, right? That is not the case for a relation, right? It's just a way to kind of relate. And this is what's referred to as a binary relation, where we're just dealing with two objects here, in this case 3 and 9. All right, so that is a relation between two numbers here. Okay, and then lastly, the different structure that we'll take a look at is this idea of graphs, right? And not graphs necessarily in like the XY plane, but graphs where here say, for example, here, Idea of graphs is something like this, right? Where these little nodes here, right? These are called vertices, right? And these are called edges. Okay, and then we'll expand on these as we kind of work through the semester. But when we think of graphs, and again, these vertices and edges can represent, they're very abstract terms. They can represent parts of a problem that we're working with, but just a very basic here, a graph would look consisting of vertices and edges. Okay.